Hi, in this video, we are going to continue our problem solving series. We start off with a problem from RMO 2019. And this problem says, suppose X is a non-zero number, such that both X power 5 and 20X plus 19 by X are rational. We have to prove that X is also rational. Okay, so we are given that X power 5 belongs to the rational number set Q, and also 20X plus 19 by X belongs to Q. We need to show that X is also belonging to the set Q. So if you think about it, it will be enough to prove that if we can show 20X minus 19 by X belongs to Q, then what will we have? Then we can add these two rational numbers and get 40X belongs to Q, which implies that X belongs to Q. So we can modify the problem, and the problem is basically proving that 20X minus 19 by X belongs to Q, right? Okay, so let's think about that. Now, since X power 5 belongs to the rational number set, it implies 1 by X power 5 also belongs to Q. And that implies basically both 20X whole power 5 and 19 by X whole power 5 belong to Q. So the reason that we are saying all this is because I want to use the identity A plus B whole power 5 or A power 5 plus B power 5, something like that, in order to conclude something about 20X minus 19 by X. So how can I do that? So what I would say is, if 20X plus 19 by X belongs to Q, that implies that 20X plus 19 by X whole square also belongs to Q. And that implies that 20X whole square plus 19 by X whole square. And the next term would be plus 2 into 20 into 19, which is integer. So this part itself will belong to Q, right? Again, if I square this also, I will be able to show that 20X whole square plus 19 by X whole square belongs to Q, which will again itself imply that 20X whole power 4 plus 19 by X whole power 4 belongs to Q. You should understand how we are getting these. When you expand it, you'll get the middle term, which is an integer. And since the square of a rational is rational, we are able to prove that the two square terms adding up together should also be rational. And we repeat the same argument one more time to prove this, right? Now what we can do is try to write the expansion of A power 5 minus B power 5. So basically I want to factorize this. So obviously A minus B is a factor. If you divide it, you will get A power 4 plus A cube B plus A square B square plus A B cube plus B power 4 here. So this is the expansion, or factorization rather. Now what we will do is we will say A is equal to 20X and B is equal to 19 by X, and write A power 5 minus B power 5. So that should be 20X power 5 minus 19 by X power 5. And remember, we had said earlier, because X power 5 belongs to Q, we can prove that 20X power 5 and 19 by X power 5 both belong to Q. So therefore, the LHS here, this part belongs to, is a rational, right? So using the expansion, it is A minus B. So it is 20X minus 19 by X. And inside you'll have 20X to the power 4 plus 20x to the power 3 into 19 by x plus 20x square into 19 by x square plus 20x into 19 by x whole cube, and finally 19 by x whole power 4. Now remember, we have already shown that 20x to the power 4 plus 19 by x to the power 4 belongs to Q. We have also shown that 20x square plus 19 by x square belongs to Q. So if you group the terms of this bracket here, the first and the last term are adding up together and they become rational. Similarly, if you think of the second term and the fourth term, what is the second term? It is 20 cube into 19x square, and the fourth term is 20 into 19 cube 1 by x square. So if you take 20 into 19 common here, you will get 20x whole square plus 19 by x whole square. And now this is rational, so this is rational. So the sum of this term and this term is rational. And this term is an integer. X square will get cancelled. So what we get is the second factor here. This whole term is a rational number. And we know that the LHS is also rational, which now implies that this must be rational. So using this factorization, we have shown that 20x minus 19 by x must belong to Q. And because 20x plus 19 by x belongs to Q, now it follows that 40x, the addition of both the terms, belongs to Q, or x belongs to Q, which was what we wanted to show. So that finishes off this problem. Let's go to the next problem. This is also RMO 2019. In this problem, we have an inequality, and the question says, let A, B, C be positive reals. One second, let me just check whether this is the correct question. Right. Right. Let A, B, C be positive reals such that A plus B plus C is equal to 1. A plus B plus C is equal to 1. We have to prove that A by A square plus B cube plus C cube plus B by B square plus C cube plus A cube plus C by C square plus A cube plus B cube is less than equal to 1 by 5 ABC. Now, this is a cyclic sum. All the variables are getting interchanged one by one. You have three terms where there is symmetry, one time with A, one time with B, and one time with C. So we can write it as a cyclic sum of A by A square plus B cube plus C cube. This sum basically incorporates all of these three terms. Now notice one thing, there is B cube and C cube, and this is A square. So this is not a homogeneous inequality. However, we can make the denominator homogeneous by using this condition. Since A plus B plus C is equal to 1, we can write it as some cyclic A by A into A square into, we multiply the A square with 1, which is A plus B plus C. So you get this, which is cyclic sum of A by, you get A cube plus B cube plus C cube plus A square into B plus C. This is what we get, right? Now, by AMGM inequality, we know that A cube plus B cube plus C cube is greater than or equal to 3ABC. This can be applied here because ABC are all positive reals, right? So therefore, the sum cyclic, this term A by A cube plus B cube plus C cube plus A square into B plus C. If you replace this with 3ABC, you will get something larger because 3ABC is smaller. So you'll get less than equal to some cyclic A by 3ABC plus A square into B plus C. Right? Correct. And we can cancel one A off from here and from here and from here, and we get less than equal to cyclic sum of 1 over 3BC plus AB plus 3BC plus AB plus AC. This is what we are getting right now, right? Okay. Now, let's do it in the next screen. So far, what we have done is our initial cyclic inequality A by A square plus B cube plus C cube. We have shown that it is less than equal to some cyclic 1 by 3BC plus AB plus AC, right? Now, this can be written as equal to cyclic sum of, if you take a ABC common here, you get a 3 by A plus 1 by B plus 1 by C. And on top you have a 1, right? Now, remember that in the problem we had to show it is less than equal to 1 by 5 ABC. Something like this we needed. So I will multiply this by 5 here and this by 5 here. So I'm getting equal to 5 by 5 ABC, 3 by A plus 1 by B plus 1 by C. This is cyclic sum. And basically we have converted this. This is equal to this. And we still have the LHS is less than equal to this term, right? Now think about it. 5 by 3 by A plus 1 by B plus 1 by C is the harmonic mean, because it can be written like this. Harmonic mean of these quantities, right? So by AM, GM, HM inequality, we know that the AM will be bigger than the HM, right? So this harmonic mean will be smaller than the arithmetic mean of these terms. So we can say 5 by 3 by A plus 1 by B plus 1 by C is less than equal to 3A plus B plus C by 5. This is the arithmetic mean of 5 numbers A, B, and C, because this was the harmonic mean of those 5 numbers, right? So we know this, so we can replace this stuff with a less than equal to 3A plus B plus C by 5, right? What does that do for us? That basically we can say we are not done right now. We can say that 3A plus B plus C is clearly less than 5A plus 5B plus 5C, because A, B, C are all positive by 5. We are not changing anything in the denominator, and we are changing the numerator and making it larger, right? So this is clearly 5 times A plus B plus C by 5, which is 1, right? So what we have shown right now is that this quantity is less than 1. So that means that it is less than cyclic sum of 1 by 5 ABC, right? And we had already shown that the LHS is less than equal to this quantity. I hope you are understanding. First, what we did was we homogenized it, used AMGM once on AQ plus BQ plus CQ. And then after simplifying a little bit, we are using AM-HM inequality to replace 5 by 3 by A plus 1 by B plus 1 by C with 3A plus B plus C by 5. And we know that 3A plus B plus C by 5 is going to be less than 5A plus 5B plus 5C by 5, which is 1. So that finishes off this problem. Let's move on to the next question. This is a number theory problem, pretty easy problem from RMO 2019. Let's look at it. For each n belonging to natural numbers, let Dn denote the GCD of n and 2019 minus n. we have to find the value of D1 plus D2 and so on till D 2018 plus D 2019. Okay, so basically our sum that we need to find out is summation I goes from 1 to 2019 DI. And now you should realize that 2019 is 3 times 673 and both of these are primes. Now also Dn is GCD of n and 2019 minus n, and from Euclid's lemma we know that this is equal to the GCD of A and B is the same as the GCD of A plus B and B. So if you do A plus B and B, here you will get GCD of 2019 and N. So Dn is the same as GCD of 2019 and N. Now think about it, depending on what your N is, the GCD of these numbers will be different. So what we can say is we have 3 cases. Dn will be 1 for all N not congruent to 3 or 673, and Dn will be 3 for all N that are congruent to 3 but not 673, and Dn will be equal to 673 for all N congruent to 673. Now all we need to do is find out how many terms of each kind are there. So these terms will be the multiples of 3 up to 2019. So there will be 672 terms like this. And there will be only 2 terms less than 2019 here. One will be 673 and one will be 1346, right? Twice of 673. And the remaining terms from 1 to 2019 will fit in this pattern because all of those numbers will be co-prime with 2019. So this will be 2019 minus 672 minus 2 terms, this many terms. So when you calculate the sum, all we have to do is add up each of these terms and how many times it occurs. So what we get is 1 into 2019 minus 672 minus 2 plus 3 into, how many times does this happen? It happens 672 times. And finally, plus 2 into 673. That is your Dn in this case, right? This happens because the prime factorization of 2019 was only 2 prime factors, 3 and 673. So those are the multiples that we need to worry about, where the GCD of n and 2019 will be different. So finally, if you evaluate this expression, you get the answer 6725. You can check the calculations. That is how we get this answer here. So hopefully you understood. This was a pretty easy one. Let's look at another problem. This is RMO 2018. And in this question, we have find the set of all real values of x, real values of not x, of a, for which the real polynomial bx is equal to x square minus 2ax plus b has real roots. We are given that p0 times p1 times p2 is not equal to 0, and p0 comma p1 comma p2 are in a geometric progression, are in GP. So we have to find the set of real values of a which satisfies all these conditions. The first condition is that the quadratic has real roots. And the second condition is that the p0, p1, p2 values of the quadratic form a GP and none of these values is 0, right? So first of all, the base condition that you can say is roots of px are real. So discriminant is greater than equal to 0, which implies for this quadratic 4a square minus 4b is greater than equal to 0. Or basically that a square is greater than equal to b. This is the first condition. And now we look at certain cases trying to understand what happens if P0 and P1 and P2 are in GP, right? So first of all, you should have P of 1 square is equal to P of 0 into P of 2. So P of 1 is actually B plus 1 minus 2A whole square is equal to P of 0 is B and P of 2 is B plus 4 minus 2A minus 4A. So we simplify this a little bit, you will get b square plus 1 plus 4a square minus 4a minus 4ab plus 2b is equal to, on the other side, b square plus 4b minus 4ab. So minus 4ab gets cancelled here, b square gets cancelled, and you are ending up getting 2b is equal to 4a square minus 4a plus 1, or b is equal to 1 by 2 of 2a minus 1 whole square. This is what we are getting here. B is equal to 1 over 2 of 2a minus 1 whole square. We can rewrite it in terms of a and say that a is equal to 1 plus root of 2b by 2, right? Or we can just, I'll just do it on the next screen. We have 2a minus 1 whole square is equal to 2b. So mod of 2a minus 1 is equal to root of 2b. And we can take two separate cases. Case 1, 2a minus 1 is greater than 0 or a is greater than half. In which case we have 2a minus 1 is equal to root of 2b. And now we apply a square is greater than equal to b condition, which was for real roots. So from here we can say that uh, a square is greater than equal to b. So from here we can say a is 1 plus root of 2b by 2 and a square will be 1 plus root over 2b whole square by 4 is greater than equal to b. This can be written as a quadratic in b. If you simplify it a little bit, it looks like 2b minus 2 times root 2b minus 1 is less than equal to 0. And this means if I take x as root over 2b, I have basically x square minus 2x minus 1 is less than equal to 0. And the solutions for this by wavy curve method, you can find x should belong to 1 minus root 2 comma 1 plus root 2, or method of intervals. Basically you can find the solution. So therefore root of 2b belongs to 0 to 1 plus root 2. Root of 2b cannot be negative. So a belongs to, a is what? 1 plus root of 2b by 2. So a belongs to 1 by 2 to 2 plus root 2 by 2. That is your solution for a, that is coming from this subcase. The subcase was for a greater than half. We applied the discriminant greater than 0 condition. Now for the second subcase, where a is less than half, you have basically minus of 2a minus 1 is equal to root 2b. We follow the same steps. We can write a as 1 minus root 2b by 2 and say that a square is greater than equal to b. From there, you get an inequality like this: 1 plus 2b minus 2 times root over 2b is greater than equal to 4b. Or basically 1 minus 2 times root of 2b is greater than equal to 2b. If you take root 2b as y, this boils down to y square plus 2y minus 1 less than equal to 0. You can check this condition, check the calculations. From here we get y belongs to minus of root 2 minus 1 to root 2 minus 1. But y was root over 2b, so actually root 2b will belong to 0 to root 2 minus 1, which implies a will belong to 2 minus root 2 by 2 till 1 by 2. So from here we are getting a range of a which is less than half, which should have happened. And overall, the solution will be the intersection of the two solution sets. So we have already gotten half to 2 plus root 2 by 2. We will say not intersection, we will say union. Union 2 minus root 2 by 2 to half. This will be the set of A for which the condition holds. The conditions hold. The set of A for which you have real roots and P0, P1, P2 form a GP. So that finishes off this problem. We looked at 4 RMO problems. We'll go over more contest problems in the next few videos. Stay tuned. If you haven't subscribed to the channel, please subscribe, like the video, and I'll see you next time with another topic.